This afternoon in the human exploration of moon and asteroids is Jake Bleacher. His presentation entitled The Effect of Portable Science Instruments on EVAs as Used by Astronauts During Geologic Exploration of the Solar System.
Okay, so I'll follow Gen here and Kelsey earlier today and talk a little bit about the broader aspects of our RISE field team. So my co-authors listed here and on the abstract were the instrument leads that we worked with, but this does include a much larger team of people from RISE and some other collaborators. So basically, you may have heard Kelsey this morning, and you just heard Gen talking about the fact that we're trying to understand how portable in situ measurements can be made in the field during human exploration of solar system objects. And so that's what we're working on. This is kind of our explanation of how we go about this. So the first part to our proposed effort is to build upon the fundamental science that we've been doing out in the field. We're mostly focused on volcanological processes. So two of the main key pieces that we're looking at are pit and cave formation. And our field team last year was focused mostly on that topic, as well as the second topic, which we exclusively focused on this field campaign, which is geochemistry and mineralogy and the alteration processes that have affected the rocks since their emplacement. So basically, as we conduct that fundamental science out in the field, we are evaluating the use of currently available portable instrumentation. And as we do that, we're learning lessons about how to make in situ measurements in the field, how to couple those with the laboratory measurements, make sure we get the right samples back to the lab, whether the lab is somewhere else on that planet, in orbit, back on the Earth, whatever that case may be. We want to make sure that the best science is to be done. So as we do that, we then learn lessons about how you use these in situ measurements and portable instrumentation, and then we drive that forward as recommendations that hopefully we can then test out with further analog campaigns in the future. So this is our field site. Just as Gen introduced earlier, it's the December 1974 flow in Kilauea. So it's to the southwest of the summit of Kilauea up here. And in 1974, the very end of the year, a series of unecheloned fissures opened up here and placed this lava flow. The lava flow is basically has this dogleg pattern because connecting the two rift zones at Kilauea is the Kauai fault system. So the fault system is different than the rift zone because the fault system has not been, we think, utilized to transport magma underground. So it's truly just a fault system. It's accommodating the spreading and linking the two rift zones, which are utilized for magma migration. So these lava flows were emplaced. They basically coalesced from these sets of fissures and then would hit these fault scarps and then flow along the fault scarp till it could get around and keep draping down. So put out about a 13-kilometer long lava flow. So I've been working there with several of my team members for about the last 6 years. We were originally funded through MAMA, and we were focused mostly on the physical processes, so trying to actually understand the lava flow and placement. So now that we have a pretty good handle on that, we've got subsequent PGG funding and then build our RISE team off of that. The goal being to use the science we've learned over those 6 years to really ask important questions about the chemistry of the lava flow and then the alteration coatings that have revealed the processes related to the gas exposure, both from the summit and along the rift zone. Okay, so our basic 2015 field operations. The way we did this was we put together a crew of 3. We had 2 trained geologists. We had Dean Epler and Deborah Hurwitz, both of whom have worked on MAMA-funded projects in Flagstaff as well as other places conducting fieldwork in similar veins of study. And then the astronaut office assigned Rick Mastracchio to our team. So he's several-time flight experience, so he was able to give us some insight as to how instrumentation might actually be used by an astronaut. So he knows what it's like, wear the suit and deal with these kinds of things. We had several key objectives here. Develop basic operations timelines, including the currently existing portable and in-situ measurements. So what we were really trying to get at was, well, if 3 people are exploring the site, how long does that take? But how long does it take if those 3 people are also using the currently available technologies? So we're trying to build that timeline, see what the influence is, because we know that, you know, an XRF in the laboratory is a great instrument, but it takes some amount of time to integrate and make and produce the results that you want to see. So the real questions out here are, how can we use instruments? Do currently available off-the-shelf instruments meet what we need? And how can we use those lessons to drive forward to make sure that when we build in-situ portable measurements and instruments, we do it right? So we've been comparing the results with the laboratory study. So about 3 years ago, we started collecting samples on our field campaigns. We've been doing the lab work to back this up over that time. And now we've been bringing in the in-situ measurements over the last 2 field seasons. And so we're really trying to get at the chemistry and the mineralogy of the rock itself, and then the coatings and alteration products on top. So the instrument teams were supporting the crew for decisions. So the point here was that the crew would go out on an EVA, and we were timing them. So they would go out to explore the outcrop or the site that we had selected. They would go out and then they would decide where they wanted an instrument measurement, and then the instrument team leads would step in and make that measurement. So what we were really recording here was people hours. We were trying to get at how long does it take. So we didn't have the time to train up all the crew members on all the different instruments that we wanted them to use. So this was our kind of proxy for having them use that. So again, we're trying to get at the timeline on this. The other really interesting part here was that talked a little bit about this in the first day, was we had this novel new idea for our outreach plan, which was to bring journalism students from Stony Brook out with us. And that was a very successful effort, I believe, and I encourage you to stop by the RISE journalism poster in the poster room. If you go straight down the hall, you basically walk into the poster. So let's move on. So what were we working with? Well, we basically broke our instruments down into 3 different groups. We had what we call the broad field of view, which I refer to as the site survey, and that would be the instrument Gen was just talking about. So this was our thermal infrared and our LiDAR, which we would set up and acquire images. Then we have the sample-specific instruments, which were XRD and XRF. So Kelsey talked a little bit about that this morning. So again, the point being that the crew members would select a site from which they wanted the measurement, and then the instrument team would step in and acquire the measurement while the crew continued to work. And we recorded that time effort as we went along. We also had overhead recon. So here's an example of our recon team. We have struggled over the last several years with trying to acquire permits to fly UAVs in the park. So we backed off of that and elected to go with kites. Nice advantage to kites is it's illegal to fly a UAV over top of your people. So we get to fly the kite over top of people. That's just an inherently positive part of flying the kite. And it can go all day as long as the wind keeps going. All of these can provide real-time or near real-time data for decision making. And again, these were current off-the-shelf technologies with some minor modifications. Okay, so the field operations, a lot of what we are doing is derived off many prior years of Desert Rats field testing. So what we're not trying to get into is how does a crew explore over long duration exploration. We've satisfied a lot of that through the Desert Rats. What we're doing now is taking from those efforts and focusing on specific parts. The Outcrop Exploration is what we were choosing to do here. This is the kind of approach we've used to get at a lot of things that were basically variables during Desert Rats, and we want to eliminate all the variables and focus on a specific problem. So in this case, the way we were envisioning this is essentially the crew arrive at a site with their vehicle, and then they would initiate some observations from basically mast-mounted instruments. So those would be the site survey instruments. And then upon completion of the site survey, the crew would then egress the vehicle. This is how Desert Rats did it. We had a set of cameras, so as soon as you arrived, you'd set the cameras to go, and then you'd do all your prep work. So we weren't looking at the prep work, we weren't looking at the vehicle preparedness, storing all your gear, going through the pressure checks for suits. We kept all that out of the timeline because Desert Rats has all of that. So we were able to focus on what we wanted. Just a point, Desert Rats had gotten into some of the instrumentation, but in the past, with Desert Rats, we focused on essentially the lab part. So the instruments were in the lab. So we've tested things like the MMI from JPL, Vapor out of Goddard, and we also use the XRF in the glove box. So now we're saying let's take the instruments out with us to help get the right ones in there. So that's kind of what we built from desert rats, and then we would go out on the EVA. And as I said, the crew would determine positions for specific measurements. We recorded the timelines. And again, the timelines don't include all of the data that are buried in the desert rats data sets. So ultimately, what we want to do then is build these timelines back into the overall desert rats timelines and really see what the effect of adding instruments is on exploration. So let's just go over some of these. The site survey instruments, in general, took about 23 minutes to acquire their data. So while the crew were prepping to go on EVA, the thermal infrared and the LiDAR were acquiring images. So we set these up on the tripods and acquired data. Here's an example site. You can see the thermal infrared cal targets, and here are the two the mast cameras, the LiDAR and the thermal infrared. So the LiDAR times we had in there included the whole setup and teardown. I'll note that the thermal infrared time was largely controlled by the heat up of the cal targets. Total EVA time for the crew when they got out and did the work was about 65 minutes, average 65 minutes on our sites. From desert rats, we had about 45 to 50, so we're right about the ballpark there. Individual XRF measurements took about 2 minutes, including the documentation and the acquisition of the data. So the crew plus the XRF time total XRF time averaged about 79 to 80 minutes. So you can see as you start adding the instruments in, that crew time starts to increase. When we ran the XRD during the test, we usually had it on at least 30 minutes to try and acquire some data. I'll talk a little bit in a minute about the fact that you have to be careful with the XRD because to get real good data, you have to run it a good bit longer. The airborne data, we basically got the kite in the air at the beginning, and so here you can see the team setting the kite up. The kite would have a camera hanging from it, and you can acquire data like this. This is very coarse compared to how far you can zoom in on it, but you can see the people on the ground. So you can get over top of them and you can really survey what's going on. From that, you can produce products like this, a KML file, so you can then project your crew location, sample collection on the mosaic that you produce. And then you can get into DTM derivation. So results from the LiDAR, what we found was if you park the vehicle and you take one LiDAR scan from that spot, had a situation where a lot of those original scans had about 80% of the scene was in shadow. One of the things that we started to look at, and this included the thermal infrared, was maybe instead of just taking one measurement from the vehicle, you would want some of these site survey instruments to be maybe on a coupled rover that you could then send out, because once you start taking a second or third LiDAR measurement, you really start buying down the shadow. It goes down rather rapidly. Or if you couple that with a DTM provided by the kite data, then you can really start to make a really detailed DTM of the area. But an advantage to the LiDAR over the kite data is that you can get into these shadowed areas. So if you're looking at an outcrop with shadow, the LiDAR punches right in there. And as you basically quantify that surface texture, you can, depending on how far away that outcrop is from your vehicle, you can get down to centimeter and even down to millimeter point spacing. So you can really get some good information, especially in sites that you can't even see in the visible. The broad field of view thermal infrared provides the ability to identify unique surfaces. So as Gen was talking about, it does take some time to process the data to really buy up the quantified accuracy. But real simple early on, you can start to make out differences within the rock units. And so that means that qualitatively you can use the data in real time to inform your decision-making process on where to collect samples or where to make other measurements. The XRF comes into this because with a contact instrument, you can then make high spatial resolution in situ mapping of the geochemical variability. So as you look at maybe a stack of sediment or ash, there are some variations throughout that. Maybe you don't want to destroy that outcrop. For instance, in Hawaii, you don't want to destroy that outcrop. So you can do measurements like this where you can map out that variability. The sulfur-rich areas at the fumaroles are the same thing. High variability in the sulfur deposits. So this is what you can really get into, and then you tie that back to the thermal infrared data. The XRD mineralogy is obviously very desirable. But sometimes to get real good measurements on multi-phase samples can take several hours to really buy down that accuracy or buy up that accuracy. So traditional XRD approach might require some modification to how we approach this. For instance, if we can develop contact XRD capabilities, that might be able to provide some rapid return that we're looking for. Now, how do we use this data? During desert rats, we had wearable computers. If you can get that wearable or that data onto your wearable computer, that really helps you to make basically the qualitative decisions that you want to make as you leave the vehicle. So that thermal infrared image is acquired, you're moving out and you can see it on your cuff and you can find that spot. That's when you can say, well, I don't know exactly what it is, but this is blue and that's red, so I need one of both. The other aspect to this that we were testing in desert rats is the role of the IV. So a person inside a habitat or a person inside the rover, they can actually work with that data and then send the information out to you. Sample over here, move off to your left about 2 meters. That's where we see the variability increasing. So the role of the IV is very important. So my last slide here, real-time qualitative use of portable and in-situ instrument data can be implemented in very beneficial ways during EVA activities. Real-time data enables high spatial resolution mapping, enables us to basically high-grade the sample selections and make sure we get the right rocks. It also provides calibration points and geologic context for the broad field of view cameras. Instrument timelines are being developed here, and we need to integrate them with the Desert Rats traverse timelines from past seasons so we can really evaluate the impact from in-situ measurements. So that's our team and what we've done, and I don't know if I have time for questions, but if not, I'd be happy to talk to you afterwards.
I think we have time for maybe one question.
Hey Jay, great talk. Paul Abel, NASA Johnson. Have you looked at integrating remote sensing data from a robotic precursor, tying that all in, so you're going from robotic precursor then to the human exploration, and coupled to that also looking at deployable instruments where you actually, they're deployed by the crew, they can integrate over a period of time, and they don't have to be science, it could be engineering, and then you pick those up, and how does that help with your sample selection or your science and your engineering?
Yep, that's an excellent question. So I focused very much on our field campaign this year. RISE, in a broader sense, has we're the second theme of RISE, the field part. The first theme is actually the remote sensing part. And so we cross over with that theme, and we've done that work over the last 6 years here, analyzing the remote sensing data to help us figure out where we wanted to go. As part of our PGG work, we've also done deployment of stations. We've actually been really interested in the wind patterns and how the gases are carried over top of these rocks. So that's a whole nother contextual piece of information that saying, well, there's gas here, that's nice, but if you don't know how it's being transported and moved around from the vents, like we've learned from our deployments of those stations, it's not as helpful. So we are tying all of that together, and it's a big mix, which is why we